The Winogradsky Column was named after the Russian scientist Sergei Winogradsky, and in every possible way, it is a tiny mini ecosystem. And within this ecosystem, we can revisit many of the metabolic strategies for life that we have already met. Let's begin at the very deep down levels of this column. Recall that when you built it in lab, you packed mud and you mixed in a newspaper as a carbon source, a source of cellulose, along with salts, things like calcium carbonate and calcium sulfate and different kinds of salts. And those all are playing a role in supporting the life of the deep dwellers. These deep dwellers are either living via fermentation, where they completely lack an electron transport chain, and a common character that is using that strategy for life is Clostridium. Yes, you have heard of it because you have heard of Clostridium botulinum, Clostridium tetani. You've talked about these in lab. Clostridium is an obligate fermenter, and it actually does ferment cellulose. So it's capable of fermenting that newspaper as a carbon source. Once it has fermented, we know that it gives off organic acids, and that can serve as a fuel source for another neighbor named D-sulfonyl vibrio. Now, D-sulfonyl vibrio lives in a similar way to what we do, in that it has an electron transport chain and it is capable of respiration. However, it respires anaerobically. So remember those sulfate salts that you put in here, where D-sulfonyl vibrio can use sulfur or sulfate as a terminal electron acceptor in its anaerobic respiration. So when that happens, of course, it's reducing the sulfur, and so we get the production of highly reduced sulfur, H2S, or the smelly rotten egg hydrogen sulfide. So deep down in the column, the concentrations of hydrogen sulfide become very, very high, and this hydrogen sulfide gas wafts its way up, and so there's a gradient, a concentration gradient of hydrogen sulfide going from high in the very bottom of the column to a little bit lower as you come up, and eventually very low at the top of the column. But the green sulfur bacteria and purple sulfur bacteria, remember that these are anoxygenic phototrophs, meaning that they don't produce oxygen, meaning that they don't strip and rip their electrons off of water, and instead their source of electrons, you guessed it, is hydrogen sulfide. So they strip their reducing power from hydrogen sulfide. Now, green sulfur bacteria can tolerate more hydrogen sulfide, and they are less capable of movement than the purple sulfur bacteria. So you see that the purple sulfur bacteria form a line above the green sulfur bacteria. Now, there are some quintessential examples of these. For example, chlorobium is an example of a green sulfur bacterium. Chromatium and Thiospirillum are purple sulfur bacteria. And then above the purple sulfur bacteria is another group of anoxygenic phototrophs called the purple non-sulfur bacteria. Now, they use organoids as their form of electron donors for their anoxygenic photosynthesis, but also purple non-sulfur bacteria are super flexible. They're capable of doing a lot of different, whatever strategies they need to use metabolically in order to survive. So they're very, very flexible. They'll keep on going even if you starve them of light. Now, if we keep coming up, the oxygenic phototrophs are present. And the oxygenic phototrophs, remember, strip their electrons off of water at their photosystem 2. Remember, they have two photosystems, photosystem 2 and photosystem 1. And at photosystem 2, they strip their electrons off of water and make oxygen gas. So the Winogradsky column is a perfect system in which to review our knowledge of photosynthesis and to see in action many of those strategies for life going on and happening right here, and the biogeochemical cycling that can take place within a micro ecosystem. Now, as we're thinking back to our oxygenic phototrophs, which, by the way, cyanobacteria is a great example. That's a very large group of organisms, but they're oxygenic phototrophs, and of course algae. Remember that we talked about the products of the light reactions of the oxygenic phototropes, the NADPH and the ATP, and how those then get consumed in the dark reactions of photosynthesis. So we talked about the Calvin cycle, and everyone remembers seeing this epic cycle that is extremely reductive, extremely endergonic. It's consuming 18 ATPs, 12 NADPH for every one carbon, six carbon sugar that it makes. So highly energy consuming. And this is how you recognize an anabolic biosynthetic pathway, is the consumption of ATP, the consumption of NADPH. So as we turn our attention to additional anabolism or anabolic pathways within the cell, keep that characteristic in mind in recognizing these. And I want to just come back to what is maybe a skeleton version of the pathways that you have drawn and built within your posters, and to remind us that some of the molecules, or many of the molecules within these largely catabolic pathways, which we labeled amphibolic pathways, because many of the intermediates, or even in some cases the products, are capable of being used as precursor metabolites in anabolic pathways. So a couple of examples of that. Pyruvate can very easily be used as a precursor metabolite to build the amino acid alanine. Likewise, we can see amino acids within the TCA cycle, or we can see intermediates within the TCA cycle being used to also build amino acids. For example, you can guess that alpha-ketoglutarate is used to biosynthesize glutamate and aspartate. Oxaloacetate can be used to biosynthesize many different amino acids, one of which is lysine. We can see succinyl-CoA being used to build porphyrins in certain organisms. And so this is another, not an amino acid, but something important in aerobic respiration. Additionally, in the pentose phosphate pathway, intermediates from the pentose phosphate pathway can be utilized to build aromatic amino acids. So there are many anabolic pathways, and let's take a look at just one. Here, remember oxaloacetate, the precursor metabolite from the TCA cycle. It's the last intermediate before acetyl-CoA enters in and citrate is made. So remember that oxaloacetate, I mentioned, could be used as a precursor metabolite to build a lot of amino acids, one of which is aspartate. But check it out, as more ATP is put in and more reducing power is put in, we can get the synthesis of things like threonine and methionine and lysine. So this very anabolic, reductive, biosynthetic pathway in which oxaloacetate is a precursor metabolite, and we see a lot of reducing power in the form of NADPH produced, and we're consuming that NADPH to continually reduce the intermediates of this biosynthetic pathway to make the amino acids. So in class today, we are going to look at an article in which we look at another reductive biosynthesis. And so I'm going to ask you to flex your sexy minds when considering a different type of anabolism.